Assalamualaikum and hi. We will be presenting our group assignment and the topic that we choose is heat exchanger. Here is the list of group members. First and foremost, the introduction part. Heat exchanger is a device that transfers heat from one medium to another. A simple example can be seen in a hydraulic oil cooler, which is this device removes heat from heated oil by utilizing cool water or air. However, to design a controller for a heat exchanger, an accurate mathematical model is required, which may be acquired from either a first principle model or a black box system identification experiment. When developing a controller, the system designer must consider numerous additional elements such as process uncertainty, measurement noise, and system robustness in addition to the mathematical model of the process. The most widely used controller is the proportional integral derivative, which is PID controller, which has a wide range of application in several fields of automated control.
Next, the objective for this project. First, to analyze the performance of different control techniques to control a regulatory control process. Second, to identify the desired performance specification of controller design for temperature control of heat exchanger. Third, to design the controller that satisfy the desired performance specification.
Next is the mathematical model. Figure 1 is the schematic diagram of heat exchanger. The experimental data available for heat exchanger system is summarized as shown. Heat exchanger response to steam flow gain is 50 degrees Celsius per kilogram per second. Time constant is 30 seconds. Exchanger response to variation of process flow gain is 1 degree Celsius per kilogram per second. Heat exchanger response to variation of process temperature gain is 3 degrees Celsius per degree Celsius. And capacity of control valve is 1.6 kilogram per second. And time constant for control valve is 3 seconds. And time constant for sensor is 10 seconds. And from this experimental data, linearized mathematical model of heat exchanger is developed. Next is the transfer function. As we can see in the slide, the transfer function for each of the system involved has been developed.
This is the complete block diagram for the heat exchanger system with full transfer function, the transfer function on the disturbance, the transfer function for the valve, the transfer function for the process, and the transfer function for the feedback, which is HS sensors. In this project, we only focus on the transfer function for the process and the feedback sensors. We neglect the valve transfer function and the disturbance transfer function. We create the block diagram from compensated closed loop when feedback equals to 1. So by assuming HS equals to 1 and K controller is unknown, so the T cycle is represented as 5KE power of negative 1s over 90s squared plus 33s plus 1 plus 5KE power of negative 1s. Then we calculate the error in the system on the process transfer function by using a step input. So the error that we calculated of the system is 16.67%. So our target error is to minimize to 10%. So the KP new we should get about 9. Then the method that we want to compensate this system is the cascade lead compensator. The percent overshoot our target is 10% and the settling time is 2 seconds. So from these two values, we got the coordinate of the poles, negative 2 plus minus j 2.728. Then from here, this is the formal equation for the cascade lead compensator, s plus zc over s plus pc. By assuming zc equals to 2, we need to find the pc. To find the pc, first we plot the coordinate, which is s equals to negative 2 plus 2.728j. Then by using root locus, we also draw the triangle here, and then we calculate the angle of theta 1 and theta 2. Note that this cycle is about 180 degree. So theta 1 is 118.68 degree, theta 2 is 126.25 degree. So to calculate the angle of deficiency refers to the angle of for the poles PC. So since that 244.93 is at 180 degree cycle, so we have to plus minus it. We get the deficiency angle 64.93 degree. So from the value of 64.93 degree, we calculate what is the coordinate to get this angle. So this is as represent as PC, which is negative 7.85. Thus our GC for cascade lead compensator S plus 2 over S plus 7.85. Then from these three values here of all poles and zeros, using formula K equals to summation of length of pole length over summation of length zero length, then we got the K is equals to 24. Then from this manual calculation of the lead compensator, cascade lead compensator, we insert it into the block diagram again with 24 as K, and this is the DC compensator transfer function. Then from both equation transfer function, first we insert the transfer function for the uncompensated closed loop gs 5e to the power negative 1s over 19s squared plus 33s plus 1. So this is the both editor graph where magnitude to the frequency and the phase to the frequency. This is the root locus, and this is the step response that we got. From this data, by using PID tuner, we know the rise time, which is 21.8 seconds, settling time 86.8 seconds, overshoot 12.1%, and peak is 1.12. Then we plot the compensated closed loop cascade lead compensator. This is the transfer function when we multiply with the calculate manual compensator to the transfer function of process. So this is the BODE editor of magnitude to frequency, phase to frequency, root locus here, and the step response. So from this data, by using the PID tuner again, the rise time is 12.5 seconds, settling time is reduced to 48.1 seconds, overshoot is reduced to 11.1%, and the peak is 1.11.
Now we go to the design compensator using SISO tool. First, write the transfer function GS in the MATLAB to get the root locus. The root locus is shown in figure 11. Then, modify the root locus with the desired settling time and percent overshoot. The settling time is 2 seconds and the overshoot is 10%. The settling time and the percent overshoot line is shown in figure 13. To modify the equivalent transfer function with the lead compensator function, the real zero is set to the value of 2 due to the earlier assumption. The real pole value is then set so that the root locus graph falls right on top of the settling timeline. The root values, which are the pink colored circle, are then dragged to the intersection between the settling timeline and the percent overshoot line. These steps can be seen in figure 15. The value of K is calculated using the zeros and poles that we get from the compensator editor. Therefore, the lead compensator transfer function is GCS equals to 27.35 times S plus 2 over S plus 8.55. Then, the transfer function is modified by multiply it with the GS. After that, write the modified transfer function in the MATLAB command window. The graph response is then generated using PID tuner and the SISO tool.
The response for the modified transfer function is shown in figure 17, and the percent overshoot is 12.3%.
After that, we will validate the calculation from previous slide using MATLAB Simulink. On figure 19, it shows for three model design in Simulink in closed-loop systems. The first design at the top one is the heat exchanger without compensator. The middle one is heat exchanger using calculation manually to get the compensator equation where K equals to 24 and with modified transfer function S plus 2 over S plus 7.85. The third one, the bottom one, is the composite using CISO tools in MATLAB, where K equal to 27.35 and modified transfer function is S plus 2 over S plus 8.55. All these three models will go to the scope to show the response of the system. Next, figure 20 is the graph response of the closed loop system for all model, where yellow lines indicates heat exchanger without compensator. The blue line is indicate using calculation manually to get compensate equation. The red line indicate compensate using CISO tool on MATLAB. The blue and red shows the response which match with the performance observed in root locus design on previous slide. This shows that using compensator can meet all the given design requirements.
In conclusion, this project deals with control heat exchanger by using compensator to produce the desired overshoot and settling time. From the analysis, we'll be able to reduce the overshoot percentage from 12.1% to 11.1% and the settling time from 86.8 seconds to 48.1 seconds. With the addition of compensator, the system will be able to manipulate the desired temperature faster and more accurately.